We're very happy to have Andriy Nevidomskyy here to give the colloquium on a subject very close to my heart, spin liquids and spin solids, a subject I've admired for decades and tried to contribute to without success, but Andriy here is a true expert. He's recipient of many honors, an NSF early career award, and many others, and a professor at Rice University. Let me transfer the mic to him.
Thank you so much, Mike. So, as you know, the goal of colloquia, the Aspen Center, is to try to introduce the subject to the various audience among the people who are not just the workshop that I happen to be organizing this week, but the people who are here from 2 other workshops. I'm going to therefore not assume that you know about the subject. I mean, obviously, we are all physicists, or at least related to physics discipline. Other than that, I ask for forgiveness if it appears that I'm insulting your intelligence and you already know all of this. Let me first explain the words in the title. I'm going to give a non-rigorous, non-mathematical definition. What I will mean by a quantum spin solid, the state that does not break the SO3 spin invariance, spin rotational invariance. So that already assumes that the Lagrangian or Hamiltonian you start with is rotationally invariant. However, it has a gap to the excitations, and in that sense, it's protected by a gap. Right? Before you ask me whether it's topological or not, this will come later. For now, that's all I'm going to assume in the definition. And so one example of a spin solid is a set of dimers, spin halves, form a singlet, and therefore preserves the SU2 rotational invariant state. And they cover a lattice. In this case, this spontaneously breaks also lattice translation and certain rotation symmetries. That's not important for today's discussion. Now, how does one get a liquid? Well, how does one melt a solid? So one idea is to try to apply temperature and therefore try and end up with a state that somehow is disordered. It's often known as a quantum or magnet, and you raise temperature high enough, it becomes classical. And you could think of it as a spin gas. What we'd really like to get is not spin gas, but a spin liquid. How do we get there? The idea is not to melt this by thermal fluctuations, but by quantum fluctuation. So today's talk is going to be about quantum solids, quantum liquids. How do you go from one to the other? But I'm going to start really basic and ask you the following question. What is spin? Now, I realize this is probably totally redundant here, but just in case, when we teach undergraduate quantum mechanics, right, the way it's introduced is either axiomatically, it's an internal quantum number of an electron. It is what it is. Do not question it. Or we give the hand-wavy explanation that you could think of an electron sort of spinning around its own axis, and then we say a bunch of words saying, yeah, there are caveats associated with that. I want to pull this picture a bit more, and historically, it goes back to these 3 gentlemen, Uhlenbeck and Sam Goudsmit. Kramers was one of the people who heard their ideas first. We're working in Leiden in the Netherlands. Around 1925, they came up with this idea, and this is the George Uhlenbeck. You could read the citations, suggesting that the force quantum number, and remember the force is after N, L, and M, this came out from the attempts to understand the anomalous Zeeman effect. So now this is all textbook material, but at the time they didn't know about this. So they thought about the electron spinning its own axis. Uhlenbeck was a young PhD student, and he was working with Sam Goudsmit on the right, who was an equivalent of a senior undergrad student. And of course, these are the caveats that I mentioned. So one objection, which actually goes back much earlier to Max Abraham in 1903, is that if you just look at what the velocity of a hypothetical classical object would be, if you imagine that the electron were classical, that would violate special relativity. That actually did not concern Uhlenbeck and Goudsmit that much. They argue that, quantum mechanics is weird, all kind of things happen. Let's not worry about this. This is not a classical object. Much more serious objection was raised by Hendrik Lorentz. Lorentz was the recipient of the Nobel Prize, hugely influential figure at the time. And when he heard of the suggestion, he said, yeah, that's not going to work. And the subtlety there was that if you try and infer what would the radius of an electron be, if you equate this to orbital momentum, and somehow the mass just didn't work out. Okay? And this was serious enough for Goudsmit and Uhlenbeck that they decided that they're going to pull out the paper. And when they came to the advisor, he said the following: unfortunately, I already sent the paper to Nature. No, the ship has sailed, but you're young enough to be able to afford the stupidity. So this is interesting words from Paul Ehrenfest. And such was the fate that the paper got accepted and got eventually published in Nature. And of course, hot on the heels of this, there was this man who, was known to not mince his words. When he heard about this, it's another heresy coming from Copenhagen. Actually, Wolfgang Pauli's objection was not so much philosophical about violation of special relativity or the radius of the electrons. It was the fact that the numbers didn't match up. It turns out that Pauli himself thought about the fourth quantum number, what we now understand as spin, and he knew that without what we now understand as a Thomas factor, same Thomas from Fermi-Thomas screening, that just didn't work. So that was actually the reason why Pauli objected to it. And you could read about this and others, for instance, in this article by Abraham Pais. But also there is so this was published in 1989, the symposium to commemorate the passing of George Uhlenbeck. Then there is also a beautiful book by Shin Ichiro Tomonaga, a famous physicist in his own right, who in the early years of his career actually worked on the Werner Heisenberg, and he met firsthand the people who were involved in the story. And so he gives a second-hand account of how this happened. Okay, so all of this under the rug, right? Now we sort of at the same level as how we understood in the 1920s, what the electron was. If you travel to Leiden nowadays, and I did it just before the pandemic and was lucky to see it, there's something called a wall formula. So is it Moore formulas? Anybody here who speaks Dutch? Don't. Okay, so you could see the names of George Uhlenbeck and Sam Goudsmit commemorated on these plaques, and you could see the electrons spinning to the left and spinning to the right. Okay. Now, what is a spin in a normal, in a current understanding? You would say it's a projective representation of a rotational group, 3 spatial dimensions, SO3. And it was Hermann Weyl who pointed out that if you want to get not just integer spins, but also half integer, you have to work a little bit harder and involve so-called spinor representation of a double cover. A bit more nuanced representation if you consider relativistic theories, and again, this is more at home to you folks who do high energy and string theory, is that it's a label of representations of Poincare group or technically universal cover of that group. And the famous statistic theorem in QFT tells us that the particles are bosons or fermions, depending on the spin. Okay. So from this perspective, there's clear distinction between, say, spin half and spin 1. One is fermion, the other is boson. But the remainder of this talk, I'm going to work in non-relativistic theories in 2+1 and 3+1 dimensions. And the question I'm going to ask is whether or not you could tell the difference between spin half and spin 1. Can anybody tell me who this gentleman is? Right. This picture is perhaps more recognizable, but I tried to find a picture from the days where Haldane actually made his conjecture. And so what Duncan Haldane did was to look at the fate of a one-dimensional spin chain and ask as to how can we understand this. It's now known as a Haldane mapping, is to decompose the spin degrees of freedom into the so-called slow and fast modes. And upon integrating the fast modes, ends up with effective theory for what here is labeled as M, that's the slow degrees of freedom. The theory has 2 terms. It's a nonlinear sigma model, so it has a constraint, which you didn't write down, but what stands in the Lagrangian is the term that looks like this, and then there is a so-called theta term. Okay. For those of you who've seen this before, this is self-explanatory, but let me slowly go step by step through what this is. So if I first forget about the theta term and ask what is the meaning of the first term, what you see here is that if you were to extract the Euler-Lagrange equation of motions, and then it's easier to see it in Fourier transform space, that what this tells you is a linear relationship of the momentum of the particle and its frequency. And this is observed, for instance, I'm not sure, are there any experimentalists in the audience? One? Only see one hand. You two, 1.5. So experimentalists in the audience, what's, you would appreciate, I did put some of the effort into trying to show you an actual data, and more recent one than going back to 1925. This is a few years back. compound, which is iron nucleotides taken by my colleague at Rice, Peng Chengai. It shows the dispersion. If you look at the spectrum near this case, the origin, which is centered at a particular value of wave vector, you see this linear dispersing modes. Okay? And these are known as the Nambu-Goldstone modes, which we know and love. And all of this makes sense. Now, what about the theta term? The term that so far I have neglected to tell you. Again, one can understand this term over here as a solid angle subtended by the vector m as it goes across around the surface of a sphere. And it's nothing else but the geometric Berry phase. Now, what I'm about to show you is that, not really proving it mathematically, I'll try to convince you this value of q is actually an integer. And to do that, let me first explain what integration is over. It's over the coordinates, which in this one-dimensional chain is just the time and the direction along the axis. And it's useful to think of this as a map that maps from R2 into a two-sphere. What will help me is if you make a stereographic projection. So if you allow for including the points at infinity, then there is a mapping between the sphere and the two-dimensional plane. So what you do is that you start from the North Pole and you project onto the point P prime somewhere on the surface. And the correspondence is that the point P on the sphere maps onto the point P prime on the surface. So after such a stereographic projection, what stands here could be understood as an integral of this map that maps a two-sphere onto a two-sphere. And this is how you could see it. By the way, this you could do at home. This is actually a hand of a person holding a mobile phone. And this is a fancy cutout. I attempted to bring one to Aspen, but it collapsed in travel, so I wasn't so successful to show you. You could see it's made of cardboard. So when you shine the point source, in this case, the camera of the cell phone, well, you could see a nice square lattice, right? That's your R2 coming from the two-sphere. If you now imagine that you have a point, a spin sitting on a square lattice somewhere here, well, it maps a dark point on the sphere. And now if you have a bunch of arrows like this, you could do the same. And now you have a mapping. I showed you a particular representation of the spins that sit on the surface of a sphere. Now, if you compute an integral like that over the two-sphere, you will find that actually the value, the map I shown here, will be equal to 0. And you have a different value? Yes, you can. For instance, this is what q equal 1 looks like. And if you stare it long enough, the only major difference apart from small changes is a so-called global topological change. And that's the fact that this spin over here points down instead of up. There's no way to go smoothly from the left picture to the picture on the right. They're distinguished by a second homotopy group, in this case of a two-sphere. And again, I'm not a mathematician. I couldn't prove it to you. Mike for sure can. The statement is that the different values of Q label different equivalence classes. So the maps from one equivalence class to the other equivalence class not be smoothly deformed to one another. For our purposes, what this means is that when we are interested in the action of nonlinear sigma model, we have to sum over all of this in equivalent topological classes, so-called topological sectors, which in this case are labeled by an integer. Now, what's interesting is that the prefactor, the value of theta standing here, is actually related to the size of the spin, right? And that was key in Haldanes mapping. What you showed is that for spin 0, 1, 2, and so on, as you could see, the value of the theta is basically 0 mod 2 pi. Since this enters in the exponential, what that really means is that all of these topological sectors summed in an identical fashion. There isn't really anything new about this theta. By contrast, if you try to do the same for the half integer spins, you will discover that actually there is an alternating sum. Okay? Now, what is the fate of this? Like, what would the result here be? Interestingly enough, even though the top result is easier to understand than the bottom, historically, it was actually the solution for the spin half chain, which was known from the algebraic beta ansatz. And goes back to the 1960s, where you could, with some work, extract the excitations and find that actually they are gaplets. And they look somewhat like this. Okay. Now, let me explain a little bit of what you're actually seeing here. It's tempting to think, just like in the case of nonlinear sigma model of Haldanes, of this being some spin waves, right? Some small excitations. This is what Haldane had in mind in his mapping. And this would be a familiar agnon or spin wave. That's not what you saw in the previous slide. In fact, what you saw here is that if you look at the spin half chain and you flip the center spin over here, you quickly realize is that you could now split. You could think of this as two domain walls that are glued together, and you could actually separate them without any extra cost in energy. So you could take these two domain walls and you could then bring them farther and farther from one another. And it's the dispersion momentum space of this domain walls that you're actually seeing. Those domain walls, also known as spin-ons, you could think of them as half of spin flip. They started with a single spin flip here in the center and ended up with two spin-ons that travel in opposite direction. Now, the experiment that I showed you earlier is done on a quasi one-dimensional compound, which the magnetic ions are actually copper. They carry spin half. It's a D9 configuration of copper. And what you see here is the inelastic neutron spectrum, where basically this is energy and this is momentum of the particles. And of course, the story is a bit more complex than that. In reality, of course, we live in a three-dimensional space. For our purposes, I'm not going to talk about space-time. And so it's actually more complicated. At low temperatures, you start being sensitive to the three-dimensional nature of these chains. Once the temperature exceeds a certain coupling between the chains, you're effectively in one-dimensional large energy liquid regime. Or I should say Tomonaga large energy liquid, the same feature of Tomonaga who I talked about before. And it's in that regime that what's interesting is that you don't just see one branch, you see a bunch of this color over here. It's non-zero intensity. Is the fact that now the two spin waves, the two spin-ons, pardon me, those two quasi-particles, they can combine in different proportions and give you a continuum of excitations, the given moment. Okay. Now, what about spin one? What I showed you was spin half. There are spin-ons, there is exotic fractionalized quasi-particle. Haldanes' conjecture was that all integer spin chains must be gapped. Now, in fact, he had it with good reason. There's work going back to Sasha Polakov explaining that if you do the RG flow, the SU2 or SU3 model, you end up that in a strong coupling, or as it flows to strong coupling, suggesting that it becomes fully gapped. Same result could be obtained with the large S limit. So if the gap is finite, what this means is that essentially correlation length is also finite, and you expect the correlation length, or rather the correlation function between the spins, decay exponentially with the set length. Any questions, by the way? I don't want to this just be in monologue. So if there are questions, please feel free to interrupt me. So we're all clear on Haldane conjecture and what this is about. And by the way, Haldane can do in one-dimensional exquisite studies. There is a concept called density matrix normalization group, which becomes essentially exact for gap phases. And this is a study I've done a number of years ago, which shows that if you expand a regular chain by including further terms such as next nearest neighbors and by quadratic terms, there's a big sways of this phase diagram here in blue. The Haldane phase is stable, and what is protected by is the gap. If you ask, what is this gap the excitations come from? This is just a side remark. There is an exactly solvable point over there. I'm going to tell you the rest of the talk. First, I told you about the conjecture, and I'm going to tell you about the theorem, and I'm going to talk about a number of examples. So, famous theorem I'm going to talk about is due to Elliott Leib, Ted Schultz, and Daniel Matisse. And essentially, the question they ask is whether one could tell a difference between spin half and spin one. And we're also interested in spin chains. The formulation of the theorem, which appeared in 1961, is here. Take a one-dimensional spin chain, or to be nice, with the even number of sites. You write down the interactions of the sort with periodic boundary conditions. The statement is that for half odd integer spins, exists an excited state with energy that vanishes in thermodynamic limit. Again, apologies for those of you who know this so-called LSM theorem by heart. In case you haven't seen it, and I'm not presuming anything, is the theorem, okay? Now, what does it actually tell you? Well, to start with, the example I just given you with the gapless excitation certainly falls to this. Right? You have a gapless excitation, right, with which disperse. There is a cone of dispersions that you see over. Now, this doesn't tell you, by the way, the system always ought to be gapless. If you read the statement of the theorem, it only tells you that there exists at least one state whose energy approaches zero in some limit. It doesn't tell you there has to be a tau of states. The one example is if you allow a breaking of spatial symmetry. This is a model which was studied by Majumdar and Ghosh a long time ago. The model with nearest and next nearest neighbors on spin half in a chain, and the solution is famously either one or second, or if you want to form a cat state, you could form a linear superposition of these two states. They have the same energy, so they satisfy the statement of the LSM theorem without actually have a gapless solution, because the rest of the excited states are separated by a nice clean gap. Now, there were the extensions to the theorem that were made to make it more general, but also extend to higher dimension. One of the protagonists sits here in the audience. Oshikawa-san, I don't see Masaki where he is. Masaki Oshikawa used topological arguments to extend the theorem to dimensions. Then a further work by Matt Hastings, the careful refined proof, with careful bounds being placed on the value of the gap in the thermodynamic limit, which was 2 and 3 dimensions, and that was state-of-the-art proof, which was also very difficult. So what the modern statement of the Lieb-Schultz-Matisse-Oshikawa-Hastings theorem is, it can be formulated as follows, and you could read it here. The spin system with integer, or half-integer, odd half-integer spins, an odd number of sides per unit cell does not admit a gap symmetric ground state like in fractionalized excitation. Okay, it's a mouthful. It tells you what it is not, right? It's not a banana. It would be more useful to tell you what it does allow. That's this statement over here. So what it tells you is that you only have 3 possibilities. I'm going to illustrate them on the next slide. You could have a broken symmetry, remember the Majumdar-Ghosh state. And this is an example of what happens in the so-called Shastri-Sutherland lattice, where the ground state is designed, Hamiltonian rather, to be designed such. The ground state is just the direct product of dimers, the non-overlapping. It's a well-defined ground state separated by a nice clear gap from the rest. Or you could have a gapless spin liquid, of which I will tell you more towards the end of the talk. An example, we'll talk more about experiment. There is only one other possibility. That's you could have a gap spin liquid. The price you pay, it must be topological. Logical in Shao-Ganwen sense, you must have long-range entanglement, you must have non-trivial topology associated with the manifold. So in a high-energy language, this is described by TUQFT. An example, for instance, is a honeycomb model designed by Kitaev. This model is not actually SO3 symmetric, but that's aside, it results in a Z2 H theory that gives you a TUQFT, right? That gives a non-trivial topology certain manifold. This is it. So the LSM Oshikawa-Hastings theorem tells you these are the only 3 possibilities you could possibly have. The theorem is completely silent about spin ones. What I'd like to tell you in the rest of the talk is what's interesting about spin ones. But before I do this, let me ask a different question. Why do you want to study spin? I mean, spin half is already a handful, and a bunch of people in our program have spent their career studying frustrated systems with pseudo spin 1/2. So why go further? And the answer is multifaceted. One is that the spin 1, while it's larger than spin half, is not large enough to be called classical. And also, the Hilbert space is larger, allowing for interesting new states such as spin nematic, which I'll tell you in a moment, literally in the next slide. And while Lieb-Schultz machine Oshikawa-Hastings theorem does not apply, it does give you freedom for actually something interesting. Haldane phase in a modern parlance is actually symmetry protected topological phase, which if you remove that symmetry is smoothly connected to a quantum paramagnet. And finally, I'm going to give you the answer, tricky answer, which was given, I guess, by who? George Mallory. When a journalist asked him why he wanted to climb Mount Everest. Well, but on a serious note, because it is there. There are compounds based on iron, nickel, cobalt that contain spin half. The story is more complicated. There's spin orbit coupling and still field effects. But effectively, you end up with the degrees of freedom that carry spin 1 rather than spin half. A bunch of these compounds, the one with the asterisk, actually lack conventional magnetic order. And it's this one that I want to emphasize why spin 1 is in some sense more interesting than spin half. See, you could choose the basis that we're used to of the principal quantum number, and this is it. Okay? But unlike spin half, if I form arbitrary linear superposition of the state, it cannot be set in somewhere on a Bloch sphere. There isn't actually a Bloch sphere, one would have to go to S3. But that aside, are configurations which don't point anywhere. By this, I mean that the expectation value of the spin components as X, as Y, as Z are identically zero. You can't do it with spin half. No matter where you point the spin on a Bloch sphere, you could always choose a basis in which the new axis, you could call it as Z, right, has a value of plus h bar over 2 or minus h bar over 2. Yeah, you can't. And in fact, if you form a linear superposition of these states, real coefficients, purely real or purely imaginary, doesn't matter. But as long as they're purely real up to a phase, end up with a state which is quadrupolar. It doesn't have any polar magnetic ordering. It only has quadrupolar moments. So what that means, by the way, is that if you try to shine neutrons on it, favorite in condensed matter physicist repertoire to try and tease out the dispersion of those objects are, you will find that actually neutrons cannot scatter off of them. There is a selection rule essentially because neutron carries spin half. A spin flip corresponds to delta S equal 1 and just doesn't couple. The magnetization is 0. There are interesting states, and this is one example. Most of this talks is not about my work, but maybe 10% is, and so this is one of example. There's a puzzle related to this material, iron selenide. It actually does not order magnetically. People couldn't understand for a while why. The best understanding we currently have that if you analyze an appropriate model that has bilinear and quadratic terms, due to rotational invariant, what you will find is that in addition to block-like solutions where you have magnetic order with a particular Q vector, or you could have regular Néel order, you also find phases that are known to be ferroquadrupolar. They lack long-range magnetic order. They still break spin rotational SO3 symmetry in a subtle way. So in that sense, it's a product state, it's a mundane, non-topological state of matter. It's tricky. It has a hidden order parameter, which is very difficult. By the way, this what I showed you was the mean field phase diagram, but DMRG confirms it wonderfully. Yes.
Is the property of being able to not point everywhere unique to spin full, or like can spin 3 halves also not point everywhere?
Correct. So the spin 3 halves, in addition to bipolar moments, can also have quadrupolar and octupolar. And you could go ad nauseam. If you go to spin 2, you could have also hexadecupolar and so on and so forth.
But just to be sure, a spin 3 halves can also have no bipolar moment.
Is correct. Yes. That is correct. So in that sense, it's not so much distinction between spin half and spin 1. It's more shameless advertising for why one shouldn't just focus on spin 1 or spin half. Spin 1s are also interesting. You could do other things. This I did not mean to do. Restart my presentation. So here you could see that. So you could see that the collective excitations in here are so-called flavor waves, and one could map them on a bunch of harmonic oscillators, gives this dynamical spin structure factor, something that you could actually measure experimentally. I just realized that as me restarting this, I'm not sure if the audience in Zoom can actually see the presentation or not. So that doesn't seem to be. I'll let Emily in the front office to see whether the audience in Zoom can see me, but at least you can. Right. So what one can show is that for these compounds, you could actually map very nicely the experimental data that you see over here. And of course, experiment has much more features as well as some experimental noise compared to the ideal idealized fluctuation theory that you could see. So I've told you so far about solids, maybe even states with long-range magnetic order like I just did. But of course, the most interesting part is about spin liquids. Right? How we do this. So let me just make sure that I'm still sharing my screen. I'll maybe reshare it to make sure that the audiences on Zoom still see it. Because I have a cunning feeling that while you guys can see it, the audience may not. So how do we actually understand what a spin liquid is and what the recipe is for it? And so again, my analogy is that, well, somehow we'd like to melt a solid, not in a literal sense, via Theorem of Brazil quantum fluctuations. One idea of how you may want to do this is to think of a liquid as a result of the quantum linear superposition of many different solid configurations. Okay. The idea goes back to the 1970s by Phil Anderson, and this became known as a resonating valence bond. To explain where the language comes from, if you remember elementary chemistry, nematic rings, in old textbooks, you could still see them being written with the double and single bonds. Well, now the modern understanding is that actually it's a linear superposition of this state and this state that actually forms the aromatic ring. Pretty much in the same fashion, imagine that except now, instead of just 2 terms in the sum, you have infinitely many of them. And the number of terms grows exponentially with the system size. You end up with sum of all of these configurations with certain width. The idea, it's really more a conjecture of Anderson, was that if you do this, you might just end up with something that would be liquid-like. Because if you look at any given spin, in one configuration, it may be related to the thing right next to it, but in this one, it's actually coupled to the one this way apart. If you sum over all such configurations, perhaps, just perhaps, might end up in a liquid-like state which lacks long-range order. So if you look again at what the picture earlier shown you, we're not so much interested in broken symmetry state. And there are 2 classes of spin liquids, gap and gapless, to which I already alluded to. For spin 1, in addition to valence bond solid, which would be a type of solid, which again is not very interesting if you're interested in liquid, you could have a spin liquid, you could have a gap spin liquid. But strictly speaking, because LSM-OH theorem does not apply to spin 1, you could have something more interesting. You could have a non-dimensionalized correlated paramagnet. Some of my colleagues would say it's boring because it's mostly deformable to a quantum paramagnet, which is just a product. And yet it's the state that if you look at it with any measurement, you wouldn't be able to see any long-range order. It wouldn't be a magnet in an ordinary sense. And so I'll give you one example of how these spin liquids can be found. This is some old map of Europe and I guess Atlantic that you see over there. I'm going to try and color it in artistic fashion. So if you're in a spin half phase space, the only objects that some theorem allows you is that you can have a spin dipolar order. It would also allow a breaking of translational symmetry or rotational symmetry, and you end up solid. If you want to have a liquid, this is some isolated islands somewhere in the Atlantic which contain either a gapless spin liquid or perhaps something like a Kitaev model, which is actually gap. Now, to add to this map, if you're now willing to include the spin 1, you have an entire rich system kind of states that break SO3 in a non-trivial fashion, and those are the quadrupolar states I alluded to earlier. Then you have this entire ocean, which could be made of these correlated quantum paramagnets, which by themselves interesting and non-trivial to study. Now, talking about gapless spin liquids, which in some ways are the most interesting ones, well, depends who you ask. It's interesting to remark that because the gap vanishes, what it also implies is that correlations do not decay exponentially, instead they decay algebraically. And there is a non-trivial question about how is it possible to start with something short range. In all the examples I told you about, we tacitly assume the Hamiltonian or Lagrangian short-ranged space. Okay, you're not allowed. It's not all talk to all. It's not SYK type physics. It's not the example of long-range models where directions decay as a power law sufficiently slowly. Here they're all short-range. So I give you a short-range physics, right? Or Hamiltonian. How can you get something which looks like this, right? The key is in the word emerge. And I'll give you one example where this happens in classical system. If you travel to Europe, there are equivalents, I believe, in the United States, of Starlings. These are the birds that form this wonderful murmurations over here. I'm going to play a video here for you. I cannot control the volume, so I have to listen to music a little bit. But so as this flocks of birds, and sometimes there is to the order of thousands of them, they form this wonderful spectacle, right? I don't know how many of you have seen something like this. And essentially, they behave, as you could see, in something that you would describe the best as some cooperative motion. Perhaps the workshop that's ongoing on liquids in many different biological and non-biological systems, perhaps you guys can answer this better than I can about how exactly this happens. I'll pick the word of this gentleman over here. This is Giorgio Parisi. About a decade ago, was marveling about starlings flying over Rome. Apparently, they're a nuisance to all the monuments and beautiful architecture. So he teamed up with people in biology at University of La Sapienza in Roma. And this is an example of a snapshot of a flock of starlings in flight. And what you see here is that there are related regions where the velocity of the starlings, so this is a 2D projection velocities, all seem to point in the same direction. And before you ask, the center of mass velocity has been subtracted. It's not like the entire flock is moving. That part has been taken. And nevertheless, you see that while the velocities overall average to 0, these two non-trivial pieces that are circled out actually seem to have a dominant velocity. It's interesting, and don't ask me how biologists know this, but apparently on average, starlings, they're sociable creatures, but they're not that social. So in a flock, one of them has only about 7 friends. These are the birds, presumably, that they are around them, that they could immediately track. And this is the velocities that they can track. If you look at the size of this region, that's definitely more than 7, right? Even better, as the flocks get better, typical size of these regions is not rare. They actually grow with the system size. And you could see it mathematically shown here. Well, if you plot correlation function as a function of distance, this ends up being a power law rather than exponential. Right? And it looks somewhat like this with some power law coefficient gamma. If you also look at the typical correlation lengths, the typical size of this region, as you look at bigger and bigger flocks of birds, it actually seems to increase with the flock size itself. So essentially, the correlation size is limited by the system size. And thermodynamic limit, of course, this would be infinite. This was my point. How do you get the algebraic spin liquid, or in this case, algebraic behavior of starlings? By the way, what's interesting here is that the exponent also ends up anomalously small. In fact, it's actually difficult to distinguish this from a log function. I would have to have more decades of scaling to be able to do it. And in their paper, this is taken the excerpt from a paper, they speculate perhaps this was an evolutionary response to starlings, perhaps predators, right? And so being able to move the entire flock, maybe a way of avoiding hawks or any other predators. This aside, if you come back to quantum spin liquids, it's an example of such a behavior, except in starlings now I want to think back about the spins. And one of the examples, which there are people here in the audience who spend decades more than me working on this, is the quantum spinosis. Yes.
For the higher people in the room, can you just spend 2 more sentences on why QED is a spin liquid?
Oh, that's not what I said. I said that QED can be an effective gauge field theory that it can be used to describe a spin liquid. And but I'll elaborate in the next 2 slides exactly on that point. You will see the answer to your question. First, let me set the premise for what the system is that I'm claiming QED can explain, describe is a better word. So historically, these are materials that form the structure, and if you stare at it, it's a bunch of tetrahedra that are corner sharing. In mineralogy, this is called a pyroclore structure. And one representative example shown here is holmium titanate, where these dots over here are the holmium atoms. The holmium has a very large spin, with spin 8. And as a result of this, what ends up happening is that the combination of certain effects, of which I don't want to dwell on, force the spins of these holmium atoms to only point along the local 111 direction. It's a mathematical jargon, but basically points either towards the center or outwards from the center of the tetrahedron. So there's Ising spins. They can only have value, if you will, of spin as z plus 8 or minus 8 using this relative axis, right? And it turns out that the constraint of the system is such that 2 of them must point in, the other 2 must point out. The analogy was made with the water ice. If you look at crystalline water ice, it actually has a structure where if you look at the neighboring 4 water molecules, there will be, so the blue here are oxygens. You will see that if there is oxygen in the center of the tetrahedron, and the other hydrogens around us, of course, want to be close to it, but because of the valence, in the end, you end up only 2 out of 4 being close. In fact, this goes back to this paper by Linus Pauling in 1935, who pointed out that if you If you look at a single tetrahedron, you could count how many ways you could arrange it, right? If there are 4 ways. He pointed out that if you now imagine looking at the network of this corner-sharing tetrahedron, you count how many microscopic states are there, satisfy 2 into out rule, grows as a power law, or exponential, I should say. And in fact, if you take a log of this, corresponding entropy, Boltzmann entropy, would correspond to log of 3/2 for each tetrahedron, or percent of each tetrahedron. So what this means is that there is a residual entropy in the system. The system keeps fluctuating, not quite settle into one state, because there is a bunch of states that are available to it that all have exactly the same energy. And so that's an example of a hugely degenerate classical ground state. In fact, you could see this residual entropy seen in the experiments. This is by measuring specific heat, and then integrating out the area under the curve in order to obtain entropy. So this discovery, which by now, and I'm sorry, I've done this again by accidentally pressing the wrong button. So when you do this, you end up with a picture asking what are the excitations in this spin liquid. So I'll explain in a second why it's spin liquid. It's because in this classical state, there is no long-range order. It behaves liquid-like. And in fact, if you look at what the excitations are, you remember those domain rules in one-dimensional chain? Equivalent of this would be that if you were to flip a single spin in a tetrahedron, that it's such that it violates this 2 in, 2 out rule, you could then separate it into 2 excitations and move them arbitrarily far away. So in a language of high energy, you would say it's a deconfined theory that describes this. In fact, this is nothing else but Maxwell electrodynamics turns out, where the individual quote-unquote charges are not electrical charges, but you could assign them as such. And when they recombine, they form an object which has 0 charge and satisfies all the Gauss rules. If you separate them far away, they're connected by an invisible string. You could also formulate this in the level of Dirac monopoles that are connected by a string. So therefore, in the language of this paper, which is by now a good 15 years old, they label them to magnetic monopoles, although perhaps description in the language of positive and negative charges is just as apt. Now, all of this was classical. Manifold, degeneracy, monopoles that move around, and they look like charges in electrostatics. How can you get quantum physics out of it? So it turns out, just like by Anderson's suggestions, that what you're allowed to do is some fluctuations between the 2 ground states. Remember the aromatic rings? You want to have these configurations where the spin arrangement, see how the red arrows point kind of clockwise, here they point counterclockwise. Both the left and the right satisfy the 2 in, 2 out rules. This is example of the 2 states that classically have the same energy. But now you could form a linear superposition. And remember that there are exponentially many such states in a system of a size n. It grows like an exponential of that system size. And so by forming a linear superposition of all the states, it was pointed out that a proper description of this is by introducing so-called ring exchange terms, and you would see why it's called a ring exchange. And the result, as I put it here, you should think of this, what the picture that I drew earlier. Here's to answer the question, what does this have to do with QED? It turns out that if you do a mapping between the spins and the corresponding electric degrees of freedom, it turns out that these ring exchanges that I drew over here can be thought of as inducing a non-zero flux through this vortex loop. And so you have a concept naturally, a magnetic field. If you go to the gauge field theory description, the vector potential. You end up with a Hamiltonian, which is described by U1 synthetic gauge theory. The only difference from physical QED that we have is that A, its Lagrangian is not relativistic. More about this in a second. And E, this Lagrangian is a compact U1 rather than non-compact QED. Does this answer the question you raised?
Maybe this is also obvious, but what protects the mass? Why doesn't the gauge field get a mass?
So when you say mass, at the moment there is no matter here. So this is the U1 degrees of freedom.
Sorry, what guarantees you? So the fact you can separate these means that you have basically the effective gauge field is massless. You have a long range.
Yes, correct. Exactly. Yeah. described by the long-range massless theory. In fact, it does have gapless excitations. In fact, you could make a mapping from quantum electrodynamics where you can introduce electric charges in the mathematical jargon that are called bosons. I already told you about magnetic monopoles. This is an example of a half spin flip. So they're called spin-ons. And then you also have gauge photons, which is precisely the gapless nature of this. The theory is gapless. And this picture is stolen from this nice review paper by Michel Gingras, who's here in the audience, the participants of our workshop. Okay, so there are different energy scales that tell you about the pair creation of the monopoles versus pair creation of bosons, and there are gapless degrees of freedom at the bottom. So I could have given, not going to, have given an entire talk about the quantum spinizers. Instead, I'm going to ask only one question, which is tell you about how the recent realization of the spinizers is probably the best non-schematic example of such a spin liquid. Based on Theorem, it was only synthesized 2019, so just before the pandemic hit. And so all the hallmark signatures of quantum spin liquids are there. There is no long-range order seen in specific heat. So for non-experts, if there was long-range order, you would typically see it as a so-called lambda transition in helium-4 in the specific. You don't see that. You see a spectrum of energy versus Q. It looks diffusive. It's like in those pictures in one-dimensional spin-ons that I mentioned here earlier. If you look at it as a map, intensity in Q space, this is Qx, this is Qy along some axis. You see that the spectral weight not centered around one point, it's kind of spread out. It's non-zero over. So this Bragg peaks is a result of a subtraction of the nuclear peaks, so never mind that. This tells you is that so this is a Fourier transform. If you transform this in real space, this tells you that the spin-spin correlations behave in algebraic fashion. And you know, this is yes, a question.
Sorry, a step back. The
Please.
Dirac screen in this case is an actual object that something weird happens in, like, right? You said there's a Dirac string. Should I think of that as like a bunch of sites pointing in some specific direction? Like,
not actually. So what happens is that once you create a spin flip and you separate it into two quasi-particles, so-called spin-ons or monopoles, all the notion of what's in between is gone. It's not unlike in Z2 gauge theories. If you take two E particles, it doesn't make sense. Ask what shape is the string connecting them. You just have two point-like excitations. So if you look far away, if you remove the other one, this is one particle. And the only way you notice that there is something strange, there must be a Dirac string attached. If you integrate the flux of the magnetic field, you find the divergence is actually non-zero. Right? So in that sense, they're monopoles.
but there are no real monopoles, right? Like in the sense that QED doesn't, you do not actually admit one. So I'm a bit confused. What actually is the way in which this breaks down?
So this is a question that I love asking my QED colleagues. I ask them, okay, so why is it you guys never study monopoles? Well, you know, so okay, so if you we are not talking, by the way, here about the 2 Polakov monopoles in SU3 that lead to, for instance, the instability of the proton. We're not talking about those, just the regular SO3, or not SO3, sorry, U1 gauge field theory monopoles. In principle, there is nothing prohibiting them from existing. Right? And from what I understand, there is an old literature in 1960s and 70s where people actually invested a bit of energy trying to write down what QED would look like if you had spin-ons, or if you had monopoles, pardon me. It's just later on, it kind of, the efforts fizzled out because my understanding, and forgive me, this is me based on me talking to my high energy colleagues, is that there wasn't sort of real reason to look for those. Right? For the best of our knowledge, we don't have, as you pointed out, monopoles in actual QED.
Yeah. You will look for them. We don't see them.
Yeah.
Yes. Okay. So right. So that succinctly summarizes the difference. It's not that QED somehow prohibits monopoles, and here we magically find them. It's just it happens that perhaps the energy scale, like a Planck scale, in which they appear in a physical world, is here they're present.
If I were to put a tiny magnetometer and go around each of these things, right? There shouldn't be an actual sum that is not, right? Gauss law would not be broken, right? I should find somewhere where this breaks down at, I don't know, the lattice length of the.
Of course. Yeah, right. So if you put a magnetometer, actually, you will see that there is an actual magnetic moment near the pole. monopoles, one here, one here. So in that sense, yes, microscopically you could measure. Of course, this is on a lattice.
C1 isn't the maximal U1 that we see in nature, right? It's something like the U1. Yeah.
Listen, well,
Magnetometer one you check as well.
okay, so there is a mapping. So the synthetic magnetic field that I'm appearing here actually has a tie to the magnetization because it starts with the spins. Yes, it's not one-to-one. Gauge field is synthetic. The photon that I mentioned is not the real photon. But the magnetic field can still be measured because the actual holmium atoms actually carry magnetic spin. Right?
You still measure multiple.
Correct. Exactly. And you could probe them. You could probe the pair production of these monopoles and see how they spread in the lattice. In that sense, it's a controlled experiment. Mapping on a compact QED is more of a mathematical tool to make it useful and precise. And this is a recent work. I won't spend more time on this, but we were able to reproduce. So what you see here on the left is the theory. What you see here superimposed at the experimental images, that you could actually see quite nicely behavior of this in a particular model we showed is a quantum spin liquid. Let me spend the remaining maybe 3 minutes of my talk about the question of, can you see photons? Can you see those gauge photons that I just mentioned, those gabless degrees of freedom? Because that would be phenomenal. Unfortunately, let me tell you straight away that nobody has seen them yet. I'll explain why. I'll also tell you about the exciting news, and this is literally fresh off the press. It's still under peer review. Perhaps we might get closer towards that prospect. Right? So can one see the synthetic? And the problem essentially is that the energy scales are very small. See, this is a picture where you have this magnetic monopole. So it turns out that this band of energy that you see here, that's this energy scale. And so in fact, would have to put it down like this for perspective, which means your photons will be somewhere over here. There is a separation of energy scale between this and this degree of freedom, relating to the perturbation theory of how the effective each theory is obtained. So in fact, if you crank the numbers for this particular compound that we studied, the scale of this blue curve that you're interested in is about 20 micro electron volts. Even for low energy, this is low. So this is about 0.2 millikelvin. That's ridiculously small. If you want the ring exchange, which gives you the typical energy scale governing the photons, it's 10 micro eV. Okay, that's small. Now, however, what one try and do, and to see if one could indirectly see the effect of the light in this physics. And the point is this: the theory is not Lorentz invariant. I mentioned it several times, in the sense that the speed of light is actually much smaller. It's slow light in some sense, compared to the energy of the corresponding quasi-particle. So in fact, as you imagine, this is energy and this is momentum by modulus. You could actually have Cherenkov-like effects because of the particle moving faster than the speed of light in the medium. So in that sense, because of this, there's the hope that perhaps if you could detect this Cherenkov radiation, you could at least indirectly point the existence of light that's strongly interacting with the matter. Now, can you do it experimentally? Well, that's the big question. You see, this until recently, I would tell you that this is impossible. But my colleagues at Scherer Institute, this is the group of Roman Sibyl and Victor Poray's grad student who poured his heart into these measurements, using something called neutron backscattering spectroscopy. It's a novel technique, which I don't have time to describe here. It has the resolution that's less than 1 microelectron. That's amazing by all standards. And so what they are able to show is the onset in the formation of excitations in this compound. Again, what you see here is an intensity plotted as a function of energy transferred from the neutron into the excitations. If you wish, this is like an absorption spectrum. What they see is a particular peak over here. And it turns out that theoretically, one could explain this curve over here. So in fact, red line is not just guides through the eye, it's a theory. It's based on a quasi-classical motion of those monopoles that we just discussed. They're moving in a particular background, and that would be related to their autocorrelation. And this fit, which was done, by the way, by Han Yan, here in the audience, working with me, where we fit the results from compact QED prediction, which includes those Cherenkov effects, to try and fit this curve The only fitting parameters that went into this effectively were the energy scales of the model. And what comes out of there in the end is that the pair production threshold to create two energetic or two spinons, right, of those monopoles. The spin production is about this many microelectron volts. That's about 11 orders of magnitude smaller than if you think of the physical QED, so then electron positron production. Right? This is a tiny miniature universe with the vastly different scales, with the speed of light that's measured in centimeters per second, units of centimeters per second, 10 to the power 10. Yes, a question.
So this is Trenka, but what about like the the Schwinger effect?
Yes. So in fact, yes. So in fact, at low energies, that's the Schwinger effects that's taken into account. If I go to the slide over here, it turns out that there is effects over here of QED just at the threshold that are taken into account. So this was work actually not by us. This is done by friend colleague Chris Laumann, and also in collaboration with the high energy people, Frank Wilczek and his postdoc. And we're able to try and write down what a compact QED prediction would be, including the Schwinger. That's exactly it. So what we are doing is, in some sense, standing on their shoulders by trying to pull this together. And what comes out from this is a concrete prediction of what the onset of the spectrum should look like. And as you can see, sort of to paraphrase Bolovic, this is a universe in a droplet, not of helium, but in a small grain of crystal. So this really brings me to conclusion. What I told you in the first part of the talk is really the story of quantum solids, quantum spin solids. I told you a story of how spin half is different from spin one and why it might be interesting to study spin one, for instance, to get a quadrupolar phase, such as that you see here. And in the second part of the talk, I try to focus more on this spin liquid effect. How do you get there? And you get there by melting the crystal by quantum fluctuation. And the effective description of this ends up being best described by some effective gauge field theory. And this prospect that perhaps one day we'd be able to see those phonons explicitly in this compact QED. But for now, stay tuned. And before I finish, let me just acknowledge my collaborators, postdocs, students, and senior colleagues with whom I collaborated, including experimentalists. And but not least, I'd like to acknowledge for inspiration, Chuck Lorre, Bill Prady. Do you know who Jim Parsons is? Yes. So the title of this talk is inspired by Fun with Spins. Thank you for your attention.
Well, very cut. Are there more questions from the audience? There were some during the lecture. Yes.
So you mentioned Trenka radiation. Is there a chance to see transition radiation?
What do you mean by transition radiation?
You have two materials usually with different refractive index, then you can, when you send kind of light from one to another, or sorry, when a charged particle crosses from one to another, you can see Trenka, right? So maybe if you create things on the edges, you start to see that thing bend around.
To be honest, not something I thought about. It's hard enough to do it on a single crystal, but hypothetically, I couldn't see why not, right? So if you imagine a wave, so-called magnetization wave traveling through a crystal, as long as you have, imagine creating an interface between two crystals, you have two different diffraction indices, you would need physically different materials, maybe like chromium titanate and dysprosium titanate, or something like this. The examples that I just gave you. But anyway, if you could imagine two materials, then hypothetically, why not? I could tell you that right now we are struggling to see light to start with in a single.
I was thinking one material versus the vacuum or whatever it is that is sitting on the outside. If you see things created on the edges, maybe.
Yeah.
Maybe you need something sent from the outside. I don't know.
Yeah. So the only way we could probe this light is not directly, right? It's not a true light source in a sense, as was pointed out. So typically surface states or surface effects are very difficult to point out. Techniques typically used like neutron scattering or muon scattering is sensitive to the volume. So you only have an edge, the fraction of the area to volume is of course scales.
Are any of the spin one compounds that you mentioned close to having an SU3 symmetry, tuning the bi-quadratic bilinear interaction? And if so, is there some interesting physics associated with that?
No to the first question, yes to the second. So no, not, oh yes. Okay. No, there isn't a particular compound that you could point out and say that is close to SU3 point. Yes, there is interesting physics. I could have given a totally different talk on SU3 physics emerging from spin 1. It's not close to so-called Tahtajan-Babujan point. It's a particular ratio happens to be 1 of biquadratic bilinear interactions, then you do see interesting things. In fact, we've shown using a state-of-the-art tensor network in MRG studies, if you start with a square lattice, seemingly unfrustrated, you put SU3 spins on it, in a sense we've just described, and actually you end up with something that looks like a spin liquid. My best guess that it's either one of those states not prohibited by LSM theorem that could be just a quantum paramagnet. An exotic explanation would be a Z3 spin liquid. You could see it because if you have SU3 objects sitting on a square lattice, natural way for them to form a singlet is to have 3 of them forming a trimer. Now, if you try to put trimers on a square lattice, you end up with the same problem as trying to put dimers on a triangle lattice. You have multiple degenerate states. If you sum over all of these configurations, you might just get a Z3 spin liquid. Yes, I could tell you more offline.
Thanks.
Maybe that's one more question.
I don't know if this is a silly question, but since you mentioned that your spin on degrees of freedom can behave as this and measuring of the rearrangement of your lattice, you can see something like an electric magnetic duality emerge here, or is that just completely out of the picture here?
Right. So in this field, we often talk about electromagnetic duality because even which field do you call magnetic and which field you call electric is in different papers, sometimes also at opposite conventions. In that sense, it's there. I'm not thinking of something, some dualities like come from high energy physics, but just at the level of Maxwell theory, yes, the duality is there. The energy scales though are different. So the how do I say, G, the interaction is not fine-tuned such that the model itself is the self-equivalent.
The magnetic charge and electric charge.
Correct. So the magnetic electric charge, if you will, are different. But
Is that a fine structure constant for your model, the ratio?
I'm glad you asked. So one thing, so this is just one slide. One thing that you could ask is that can you extract the fine structure constant? That would be really interesting. It turns out that from the existing experiment, we cannot. We could get the interaction strengths of the QED in absolute units for this particular material. You would get the speed of light, again, in absolute units. I haven't bothered computing it in centimeter per second, but you could. Everything here is known. What you lack, effectively, what is the charge of your spin? Charge in the sense of QED charge, or equivalently, what is E squared over C? And that remains undetermined. There are some suggestions from purely numerical literature. Simulating this model, it would appear that you could get alpha to be close to 0.1. That's purely numerical statement. Experimentally, on the existing data, we do not have the resolution to be able to extract it.
Well, why don't we thank Andriy once more time? And many more questions in the back.